So the second aspect is global spatial autocorrelation. We'll be interested in the notion of clustering, which is a characteristic of the overall pattern of the data. And there's quite a bit of material, and I have more detail in the slides and also in the handouts that are on the course site than I'm willing to discuss here in class. Specifically, I have a lot of the full expression for some of the means and the variances of these statistics, which we're not going to derive or is just for your information so that you have something to look it up. But we'll start with the general statistic, the general cross-product statistic, the gamma statistic, and then, which is generic, it's not necessarily spatial. Then we'll see how we turn that statistic into a spatial statistic, or a general spatial statistic, and then see how each of the well-known statistics, and specifically the joint count, the Moran's I, and Geary C, are actually nothing but special cases of this gamma statistic, or general cross-product statistic. And then for Moran's I, we'll see a way to visualize it, which is the Moran scatter plot, which is basically the way that GeoDa implements the Moran's I. The gamma statistics really come out of psychometrics. It is originally was thought of as a way to compare similarity matrices. So instead of working with just a simple vector of observations, you're working with a matrix of similarities or distances or dissimilarities. So the essence is that you're comparing a number of objects. For example, if you have students in a class and you have two ways of testing them, and you're interested in how the similarity between the students on these two types of tests are the same or are different. Basically, you measure, think of a distance measure, you have an economic distance measure and, say, a physical distance measure. Are these distances the same or are they different? And that is basically what is behind it. So the reference point, which we've always had before, was spatial randomness. Here the reference point is random matching. If there is no systematic patterning going on here, then we can randomly match these objects. And this will be the basis, again, for permutation or randomization, shuffling the data around. So how does this actually work? It works by means of these two matrices of similarity or proximity matrices for each pair of objects. So we start with, as before, n objects, and we look at them in terms of pairs, and look at how they rate on the similarity matrix or proximity matrix. So one we call matrix A, and the measure for the pair ij is aij. The other one we call B, and the measure of similarity or dissimilarity is bij. And then the statistic is a product of these two. So the product of aij and the matching bij. So if you think of two matrices as two like checkerboards, and you just put them behind each other, line them up, and you just drill straight through the same cell and multiply the values in these cells with each other, and then you add them all up. And that number, so the sum of all these cross products, actually provides you with some information about the matching. And just think about it. If there is some kind of systematic association between the two, then the products will tend to be large numbers with large numbers or small numbers with small numbers, not some kind of random matching of large and small and large. And so that is the principle behind inference for this kind of statistic. Under random matching, we can simulate what the reference distribution of the statistic would be. And it's always the same thing. We're going to shuffle things around, recompute the statistic over and over and over again. That gives us a reference distribution, and then we compare the one that we actually observe for our data to that reference distribution. We've seen this principle now several times. We've seen it with the envelopes and the K functions, and these other functions. We've seen it, we talked about it last week when we talked about the null hypothesis of spatial randomness, what that meant. So it's always the same idea. Now, how does this then become a spatial autocorrelation test, or a test for spatial matching? It's very simple. What is the A and the B? Instead of having A and B being some kind of psychological proximity matrix, we take A as a value attribute similarity, and we take B as locational similarity. Remember, that was the fundamental definition that we used for spatial autocorrelation statistics, generically, is some combination of attribute similarity with locational similarity. And since we've already seen that locational similarity can be formalized in a spatial weights matrix, that gives us one of these two matrices as our W, or spatial weights matrix. And then the other one is basically whatever measure of similarity we want to come up with. And so you can readily see that a whole number of spatial statistics for spatial autocorrelation, can be constructed using this principle. I mean, not only, we already know, not only can you take different weights matrices, but you can also take different similarity matrices. And we build them up, for example, by taking the cross product. So it's important to remember that the element of the matrix pertains to a pair, an IJ pair. Now, how we get there is by taking the observed value for I and the observed value for J and, say, multiplying them together, or taking their square difference or their absolute difference. And that then gives us a statistic in the sense of a summary of the data, which is the sum over all pairs ij of wij multiplied with aij. Now think about this for a second. When you did the spatial weights in the lab, and we talked about this a little bit last week, one characteristic of the weights matrix is that there's lots of zeros in it. It's only non-zero for the pairs that are actually neighbors. So what is going on in here, in this product? A lot of these W's will in fact be zero. So then the aij is not getting counted. So in essence, what this is a weighted sum of the aij's, which are a measure of similarity, where the weights are our spatial weights. And of course, when they're zero, it doesn't matter. It gets zeroed out. It doesn't get counted. Okay. Keep that in mind, because it's going to be a natural transition to this first statistic that we'll discuss, this joint count statistic. So what's going on here is we take as a two matrices, one a weights matrix, which of course has a bunch of zeros in it, and then another one, this similarity matrix, cross product, square difference, absolute difference, something with angles. I mean, there's a whole bunch of these statistics. These are the three main ones. And so then once we have these aij measures, we just add them up, weighted by these spatial weights. And that gives us a number. Okay. Now, how do we know whether this number is meaningful or not? And maybe I should point out, this number depends on the scale of the xi and the xj. This does not look anything like a correlation coefficient, the one that you're used to between -1 and +1, always less than 1. This could be 10 million. It all depends what units your xi and your xj are expressed in. If you do GDP for countries and you multiply them together, those are going to be very big numbers. Now, does that necessarily mean that a gamma statistic of 30 trillion is significant? No. To get the significance, you have to construct a reference distribution. So basically what we would have to do is shuffle the countries around randomly and randomly assign them with a GDP, then recalculate the gamma statistic. Do this many, many times so that we have at least 99, maybe 999, so that we get a sense of what this number is distributed like for spatial randomness. And so whatever I said, 30 trillion, if our distribution stops at around 5 trillion, then we know this is way out. So we reject a no. But if it goes up to 55 trillion, then it's, you know, pretty much in the distribution, so then we cannot reject the null hypothesis. That's the rationale. So it's a very easy way to, if you wish, make your own test. You could say, well, I don't like square roots, I like fourth root better, fourth power better. So I have a new statistic, which is now xi minus xj to the fourth power multiplied by wij. Of course, the numbers will be different. Your inference may be different because you're exaggerating differences more, and it gives you a new statistic. Is this better or worse? It depends. It depends on the power of the statistic for particular alternative hypotheses that you might be interested in. And as it turns out, the one with the most power turns out to be the cross-product statistic. In many experiments, this has been found to be the case. So just to repeat our randomization process, as I mentioned, we will, the goal is to come up with an empirical distribution function which we obtain by shuffling the objects around, recomputing these statistics, and then comparing what we observed, the gamma that we observed, to the reference distribution. Just one aside on the notion of pseudo-significance. Just remember always that this is pseudo. This is not for real. It's just a summary that makes it easier for us to discuss the results. But strictly speaking, the only thing that matters is the full reference distribution and how your statistic is relative to that full reference distribution. This is a shortcut in that it counts the number of times that the simulated statistic, the one that we get from reshuffling the data, is larger than or equal to the one that we observed. So the gamma here would be our 30 trillion, and then this would be whatever we compute for a randomly assigned global economy, where we reshuffle the countries and randomly give them different GDPs. So we get T of these, plus the one that we observe, and we divide that by the m times that we replicate this, plus the one that we observe. And that's the reason why m is always a nice number like 99 or 999, because if you add 1 to it, it's an easy ratio to make. And it looks very comparable to the kinds of p-values that you're used to, of 0.01 or 0.001 and so on. Now, it's a pseudo-significance in two important senses. One is that it depends on a random number generator. So if you do this twice, you may get slightly different results. Usually, if you do it enough times, it will be more or less stable, but it will be different. So if you compute this, especially if you only do 99 replications, it could very well be that in one set of replications, say 3 are larger or equal than the observed one, so t is 3, and in another replication, t is 4. Okay. That is just because of the randomness of the random permutations. So be very careful before you start drawing very strong conclusions from these pseudo-significance levels, that at the very least you have some sense, and I want you to do this in your assignment as well, you have some sense of the sensitivity of the result. So if you bump it up to 999, how much does it change? Now the second aspect is that don't get fooled by the numbers, because when you do 99 permutations, what is the most significant situation you can get? So m is 99. What is the most the most extreme case is that t is what? 0. Right? No, nothing is equal to or larger than the observed one. The observed one is the tail of the distribution. Right? Everything is less than that. So if t is 0 and m is 99, the p-value is 1 over 100. It's 0.01. You can't do any better than that. It's impossible by the nature of the process that we follow. Okay. Now then, you bump it up to 999, and you get the same result in terms of t. T again is 0. Now it's your p-value. 1 over 1,000. Is this more significant? No. It's the same. In both cases, you do not find a single replicated value that is larger than or equal to the one that you observe. So this is something you have to be careful with when interpreting and writing up your results. These two situations are not in the classical sense, where your p-value is based on a formal probability distribution and an analytical result. Then if you have a p-value of 0.001 compared to 0.01, the first one is more significant. No discussion. Here, that's not the case. Here, you should never say that. You should always be very careful in interpreting pseudo-significance values, because they're dependent. They obviously depend on the data only, but they also depend on the randomization, how good is your random number generator, and they depend on the number of replications that you use. So this should really be used as a qualitative guideline, in the sense that if you find 0.10 for one weights matrix and 0.001 for another weights matrix, using the same number of replications, you know that one is significant, the other one is not. But if you don't use the same number of replications, these numbers are not comparable. Also, as we'll see later, if you don't use the same weights matrices for different variables, then they're not comparable. So you have to always, and we mentioned that last week too, always take the statistic together with the weights. Because, I mean, it shows you very nicely here, it is the product of the weights with the attribute similarity. So you can have different variables that will affect the A, or you can have different weights that will affect the W, which means that these numbers, those gammas that come out of there, are not necessarily comparable. Now let's see a special case of this, one of the classic spatial autocorrelation statistics, the join count statistic. And what the join count statistic does is counting joins. And we'll see what that means in a second. This statistic is relevant in a specific context of binary data. And binary data are ones that take on two values. Typically presence or absence, 1 or 0, black or white, something like that. Now, it's important to keep in mind, this is not the same as the events that we had. With the events, we only got the ones. We didn't get the zeros. We're trying to replicate the zeros in the case control setup, but it's still not the same, because these are not all the possible zeros. In this case, discrete spatial data, we have all the points. So this would be a case where, say, rather than, let me just paraphrase it, if you're looking at crime, and which we did in some of our examples, we had the locations of where the crimes were committed, and then we took those as event data. Now in this case, to use this kind of approach, what you would have to do is cut up your city into discrete segments, say each street block or each segment of a street block, And then for each of these segments, observe whether or not a crime took place. So the street with a crime would get a 1, the street without a crime would get a 0. In a point pattern analysis, the street without a crime never came into play. It was not used. That's the main difference between the two. So if you have sufficient information and you have meaningful ways to make your space discrete, so to speak, then this kind of analysis can be used. And in fact, there's some literature looking at, for example, vehicle accidents on highways. There's two ways in which you can look at vehicle accidents. One is the point pattern analysis way. You have the location where the accidents happen. Another one is to take these, whatever they call them, these quarter miles or these mile segments on all the highways, and for each of these segments record whether or not an accident happened there. That's this one. You're essentially turning your space into discrete segments, and for each of these segments you have an observation on whether or not the event happened. So these two approaches are two different ways of dealing with space. So unlike the events, all the locations are observed. So what we need to do is come up with a statistic that combines our location, our W, with our attribute similarity. And what this will boil down to in this particular case is, as I mentioned, counting the joins. The joins in value that match the joins in space. In other words, those cases where neighbors have the same values. So you have two segments on your road, and in each segment there was an accident. Or in each segment there was no accident. Or then the opposite, which is negative spatial autocorrelation. One segment had an accident, the next one did not. So we have these as ones and zeros. So now we have to think, how do we get our ones and zeros into that AIJ that we need for our statistic? Okay. Think about this for a second. The statistic was a weighted sum of our AIJs. So we have to come up with AIJs that can actually be added up. And we'll add them up because WIJ will be non-zero for the neighbor. So by definition, we're only counting the non-zeros. We're only counting the joins. We're only counting the situations where I and J are neighbors. So to get to our value measure, we distinguish between three situations. As I mentioned, two of these are positive autocorrelation, presence-presence, or BB as it's called in the literature, black-black, or absence-absence, WW. Of course, what you call presence or absence is up to you. These are categorical variables with two categories. Okay? It doesn't have to be presence or absence. I mean, the outcome could be, say, red and blue. Right? So one is red, the other one is blue. Red states, blue states. Right? So you're interested in the cases where red is next to red or blue is next to blue. And then negative spatial autocorrelation is our checkerboard pattern, the opposites. So those are the cases where red is next to blue or blue is next to red. Now, we don't have red and blue, we have 1 and 0. How do we turn the 1 and 0 into something that gets counted? We just have to make sure that it's not 0. We have to make sure that it's 1. And then the 1s get counted for those cases where WIJ is not 0, which in other words is for the neighbors. The BB situation, we have two 1s. How do you count two 1s? You multiply them with each other, that counts it. If you subtract them, they won't get counted. So the similarity measure that we use to capture this is the cross product of the two values. So xi and xj, if they're both 1, then we count this as a 1. If one of them is 0, or both of them are 0, we don't count it. Then let's go to the next situation, which is the complement, the zeros. Now we can't multiply the zeros together because they won't get counted that way. So we take the transform 1 minus 0, which in effect turns a 0 into a 1, and then we're back in the multiplication. So all the zeros subtracted from 1 become 1. If it's a 1 subtracted from 1, it becomes a 0. So that's the exact complement of the previous situation where we just multiplied the 1s. Here we're just turning the zeros into 1s and then multiplying. So the WW join count will count the number of situations where two neighboring locations each have a 0, and we count them by taking 1 minus xi times 1 minus xj. Then the negative autocorrelation, now we're interested in differences. So now we have to count them when they're not the same. So again, we can't multiply them, because if they're not the same, one of them will be 0, and that will cancel it out. So we have to make sure that whatever expression we use for this doesn't give us a 0 when the two are different. And the way we do that is by subtracting them and squaring the difference. So when they're different, one of them is 1 and one of them is 0. So the difference between the two, apart from the sign, is always going to be 1. So if you take the square or you take the absolute difference, same thing. So then formally, this gives us a way to build our statistic. Our statistic is Wij, which we know how to do, times Aij. And here we found 3 specific expressions for Aij. One for the BB join, xi times xj. One for the WW join, the complement, the product of the complements. And one for dissimilarity, which is the difference with the sign taken out, either by squaring it or taking the absolute value. It really doesn't make a difference because they're just ones anyway. Whether you take the square of 1 or the absolute value of 1 or minus 1, it's the same thing. Okay. Later, of course, it won't be the same when we allow continuous value, but for the discrete, it's the same. Now this exhausts all the possibilities. There's 2 things here. One is we're only counting where Wij is non-zero. So we're only counting for the neighbors. And then what are we counting? We're counting ones. We're counting those situations where one of these expressions gives us a 1. So if we do each of these separately and add it up, what do we end up with? All the total possible number of neighbors. Because each pair of neighbors is one of these 3 categories. It's either 1 next to 1, 0 next to 0, or 1 next to 0. So the 3 statistics, and we'll call them the BB joint count, the WW joint count, and the BW joint count. Those 3 together add up to the sum of the weights. So when you do 2 of them, you know the third. You don't have to do all 3. By definition, because it's a double sum over all the weights, and the only thing you're summing is the weights themselves for the 3 different situations which exhaust all the possibilities. Okay, traditionally then, we'll see in a second what they are. Let me show you an example. This is a real data set of independence in African countries in 1950, which is a long time ago. But in 1950, some countries were independent, some were not. Most of them became independent through the late 50s and early 60s. By 1960, most of them were independent, but in 1950, they were not. The question is this patterning? And this is where, again, we have to watch out for our brain pattern recognizer, because I would argue that most reasonable people would see this as one big cluster here. and would therefore conclude that the independent countries would tend to show a clustering in the overall country, in the overall continent. And we'll see if that's the case or not. And here, randomized, I'll have to fix that. This is randomly assigned. So we have a fixed number of independent countries, and now we are randomly throwing them on the map. And we're rewriting history, and these are now the countries that we make independent at that time. What is the BB count? So we're counting the number of times that two of these red ones border each other. So these ones are out, and it's all happening in here. We get a total of 18. If we do it randomly, we get a total of 9. So then what we want to do is do this many, many times, and then be able to conclude, is this significant or not? Before we do that, let's get the formal expressions down. So by tradition, the weights are taken as 0, 1 as well. This just keeps it easy. You no row standardizing or any of that stuff. So we're just simply counting non-zero WIJs, which are 1, and our joins, value joins, which are 1 as well. And they're either the cross product, this will pick up the ones where 1 is next to 1, the complement of the product of the complements, which will pick up the ones where 0 is next to 0, and then these squares, which will pick up the ones where 0 is next to 1. And if we add these up, we get half of the sum of all the weights. Now, by convention, these get divided by 2, but whether or not you do this is irrelevant, as long as you remember. Okay. So it's exactly the same result in terms of significance, whether or not you divide it by 2. This S0 is something that we will encounter multiple times. It is a characteristic of the weights matrix, a simple one, namely the sum of all the weights. So the sum of all the non-zero neighbor pairs in the African continent, that is the sum, S0. So each of these neighbor pairs is either a neighbor pair of 2 independent countries, a neighbor pair of 2 non-independent countries, or a neighbor pair where 1 is independent and 1 is not. That's it. That's all there is. Okay. So therefore, we find that these add together to the total sum of the weights matrix. So how do we know that these are significant? There are 2 approaches. The easiest one is the one we already know, is the permutation. We'll just shuffle them around and recompute this. There's also some analytical ways to approach this, because this is, drawing balls out of a bag, right? You have 2 values. You have red balls and white balls, and you draw them out of the bag. What is the probability that, think of this, a red ball is followed by another red ball. It's the same kind of logic, but now put in space. So you can take the same logic that I'm sure you've all went through this in your intro stats courses, computing what is the probability that you get 3 red balls in a row when you pull them out of a bag with, half red, half white. You can compute this using the binomial distribution. All that we're adding here to this process of sampling, from a given set of combinations of 2 values, is putting them on a location. And then the question is, do we predetermine how many red balls and white balls there are? Do we fix that, or do we just give it a probability? And we've already seen, several of you have encountered this kind of situation in your point pattern simulations, because you try to mimic the same number of points as in the observed one, and in some of the simulations you mimic the intensity, but then the actual number of points that you get was not exactly the same. So that is the free sampling case. In non-free sampling, you constrain the red balls and the white balls, so to speak, to mimic the observed pattern. So that is the case if we take the countries in Africa, whatever, there's like 30 something, and we know exactly how many are independent and how many not, we don't mess with them. So then we just draw from that collection, and we either draw a red one or a white one, and we stick it in a particular location. And that again is a binomial distribution, so you can derive the probability that you observe a particular joint count statistic using that framework. We won't go into this. What we will be using is our familiar randomization permutation framework with the pseudo-significant. And in this particular example, this is actually what we get. So it's a lot less significant, if you wish, than what you might have expected just looking at the math. The p-value is only 0.04. So if we look at this distribution, and I think this was just based on, I can't remember how many there were, but let's say there were 99, that means we have 4 values that are 18 or higher. So the total is 100. We have, 3 values that are equal or higher. So t is 1, t is 3, plus 1, divided by m99 plus 1. So when we get for a round number of 100, and you get something like this, you know exactly how many are larger than or equal to the observed. Okay? And that's why we use these weird numbers, 99 and 999. If you use 999 and you get 0.004, then you have 3 that are equal to or more extreme than the one that you observe. The best you can do would be 0.001. Can't do any better than that. So that's the principle behind the joint count statistic. And we'll just keep on moving on, and now we'll let go of the categorical nature of the data, the binary nature of the data, and now the x will become a continuously distributed variable. And then we'll need to adjust our statistic. But we won't adjust it much. In fact, basically what we'll do is use the same idea of a cross-product statistic, but then apply it to a continuously distributed variable. And that gives us Marianza.
How do you detect negative spatial autocorrelation if you use BB?
You don't.
Do you have to actually go to the...
Yeah, so the one thing with the joint count statistics is that each of these statistics has a specific alternative. The null hypothesis is always spatial randomness, but the alternative is that ones cluster, or zeros cluster, or ones are next to zeros.